welcome in our studio in Hilversum. My name is Renald, I'm your host today. And joining me now for this session is not one but two guests, Santiago, Ruiz and Marcel, Raas. Welcome, guys.
Thank you.
Thank you very much.
You're welcome. Santiago, you have a background in industrial engineering, operations research, data science, and in the last years you have worked extensively with computer vision, especially on this project. Marcel, you have a background as a PhD at CERN, and you worked at companies like Shell and ASML in data, and at GoDataDriven you did a lot of different projects, right? From demand forecasting to money laundering detection, and now you're already 1.5 years on this project.
Yes.
And for those of you who do not know, Schiphol is also last year it was the second largest airport in Europe, measured to the number of flights. It hosts 104 airlines flying to 97 countries, 332 direct destinations. And one of the ambitions of Schiphol is to become an autonomous airport where decisions are supported by data and AI to improve stuff like safety, experience, but also the sustainability. So that is quite ambitious, right?
Yeah, definitely.
Hey, so the goal of data science, artificial intelligence, I mentioned a couple of directions. What can you tell us about it?
Indeed. So for Schiphol, it's a big ambition to become autonomous airport.
Yeah.
We want to realize this ambition in 2050. And you can imagine that a lot of these data-driven solutions are basically done by machine learning.
Yeah.
Therefore, for us, it's very important to have data science in place. And for example, it's not only about have all these kind of fancy algorithms working and so on, but it's also about improving the customer experience,
yeah,
and also reduce the CO2 emissions. One of the applications that we have today, we don't need to wait until 2050, is that actually we are detecting in real time many activities of the turnaround process. The turnaround process is basically all the activities that are needed to prepare a flight.
Mm-hmm.
So this is the project that Marcel and myself have been working on the last couple of years by now. Yeah.
Yeah. So the turnaround process is about the refueling, getting baggage in, baggage out. Yeah. Is there something that you can show us?
Yeah, definitely. So, of course, we have some internal promotion video that about the project, and I think that describes the project very well. So let's start actually with showing that first.
Schiphol is always looking to optimize its operations. To keep delivering excellent service to more and more travelers, smarter collaboration with partners and improved predictability are essential. Which is why we are gathering end-to-end insights from arrival to departure and every step in between. One of these steps contains the turnaround processes at the stand, such as fueling, cleaning, catering services, and baggage handling. Deep Turnaround uses computer vision and deep learning to identify the different turnaround processes. It works like this. Real-time video captured at the aircraft stand is analyzed by neural networks. The system recognizes different processes and times how long they take. In the future, deep turnaround data will be available real-time for the entire sector. This way, we always know what's going on, and we will be able to respond adequately on evolving issues. By combining end-to-end insights with artificial intelligence, we can predict our near future, and by sharing this data, we strengthen our collaboration, which means more on-time arrivals and departures, and excellent quality of service for our passengers.
Nice, well done. Yeah.
Looks pretty nice, huh? I would say so as well.
It's slick.
Yeah, it's
nice.
slick.
I like it. Hey, and of course, we're going into the technical details. It's GoData versus Club Cloud. It's about technology. But I was wondering, what type of business problem are you actually solving?
Of course, I think it's a valid question. No matter how fancy the tech is, I think you should always be asking this question. So one of the things that already was mentioned in the movie is the on-time performance. That's a very critical thing for Schiphol. Schiphol needs to have this as good as possible done. And on-time performance basically means what's the percentage of flights that actually depart in time, as it says. And of course, you can have many different reasons why a plane departs too late. One of them could be that it comes in too late, and another one could be that there's maybe some capacity problem in the runway. But Schiphol has analyzed these things, and the turnaround process was a big chunk of causing the delays. And of course, you can try to optimize the turnaround process by standing in front of the window, looking at it, making notes, and of course that will work at some level, but it doesn't show you the bigger patterns that are underlying what is causing it in 50% of the time or 20% of the time. You don't know. So we want to be able to get that insights, and in addition to those insights, we also have a more direct approach to it, and that's via dashboarding. So Schiphol has to work together with airlines and handlers, and these handlers actually, and those are the parties that are responsible for this process. So this dashboard, for instance, that we show here, shows, for instance, the whole H pier, which is one pier in Schiphol, and you can see all the now 2 aircraft being parked at the time when we took this screenshot. And for instance, we highlighted below the plane, and you can actually see that, for instance, fueling is going on. There are stairs connected, and you see also this Gantt chart on the right, which indicates all the different things that we are detecting. There are 33 tasks that we detect. And in the red, we have highlighted some warnings as well. So the handler can actually look at the dashboard, call someone, hey, why is the tug not here yet? Get the pushback going.
Yeah. So you're opening the black box, so to speak.
Indeed. Yeah.
And you mentioned currently it's a lot of note taking. You're trying to change that. I was wondering, Santiago. So you went for computer vision. Why not use IoT?
That's a good question. Actually, if you think about it, as Marcel already mentioned, we are detecting 33 different tasks. If you want to have a similar kind of information, you need to install different sensors in different vehicles. That's not the only problem. We also work with different handlers and with different airlines, as you already mentioned. And Schiphol needs to basically ask them to give them the data. And you can imagine that different companies have different databases and so on. So it will imply a tremendous amount of effort to keep the information in place, properly. With our solution, you only need a couple of cameras, and that's it. Plug and go.
Yeah, that's it. Fast forward 1.5 years later, of course. We've worked on it for quite some time. Schiphol's worked on it for quite some time. How does the model look like? Can you show us the model in action, so to speak?
Well, let's have a look at that. So that's a nice thing about computer vision. You can visualize it very easily. So what we created a movie here of a turnaround that's in progress, and you can actually see the on the top left, on the top you see actually the movies, the image of, and then
the actual
below
footage, right?
The actual footage, and the detections below it. So you see actually the first two. I guess no one can really read everything. I'm not going to read out everything, but you see in the top, you see aircraft appears and aircraft stops in position. So those are the two bars on the top. And then below that, you see, for instance, a couple of bars related to baggage handling, like the belt loader that actually provides the suitcases into the plane, as well as the actual loading process itself. Also, the fuel truck is indicated. You have three bars with respect to that. So we have first that the fuel truck should appear, then the fuel truck should connect, and then or it should be in position, and then it should connect. So you have like these 3 bars that you can see over there as well, with respect to the fueling. And then there are other things like for instance, the bridges, the passenger bridges, whether they are connected or not. And you also have like the power connected and whether the pushback is going on. So all these different processes, all these different tasks concerning the process are detected in this picture.
Yeah, yeah. And what was the most difficult technical challenge you had to tackle?
Yeah. So we've composed a little slide of that as well. So I think that it's really a big data challenge that we're solving together with the engineers who also did an amazing job here. So we have now 21 ramps connected. Each of these ramps have 2 cameras, and those have an image snap every 5 seconds, and that 24/7. So you can imagine that this actually has a lot of this keeps on going. So we grow our data store by 540 gigs per week currently. And since the start of the project, we started with just one ramp, 2 cameras, and then we slowly are growing. But we have now 32 gigs of data, maybe 33 at the moment, and we'll scale up to 50 ramps soon. Actually, we're in the process of doing that, so we'll be much bigger than we are now. And in addition, so we also need to predict these 33 tasks all at the same time. We try to do that as good as possible. But I think the nicest statistics actually in the top right. So that says that we have 208 days of annotated data. So that means that if you would sit in a cinema and watch all the turnaround footage that was annotated, you'll spend 208 days sitting there.
Quite an interesting movie. That's annotation. What does that mean? How did you get to 208 days of annotated data, Santiago?
Yeah, basically we have a team of dedicated and with experienced annotated team, and so because they are very experienced by now, like they have been working with us for a couple of years, and so they annotate quite efficiently. Also, we have developed in-house annotation tool, and because of the particularities of the machine learning approach that we decide to follow to solve this problem, we only need to define the start and the end of different events, and automatically you will label many OR images. So that also makes the annotation process very, very efficient. Well, we also, and this is only possible because we are basically solving an action recognition problem, which is the equivalent to this model is image classification. You might also wondering perhaps if what about other different approaches? Because this is important. I think it was a learning from our project that we did this. So at the beginning of the project, we decided to go for object detection. But soon enough, we realized that, first of all, annotating many different tasks is super labor intensive, especially compared with the current approach. And also, for example, if you want to detect certain particular task, like for example, if a vehicle is in the ramp, you will need to process the raw data. It's not something that you get directly as we do it today.
Yeah. So if I understand you correctly, instead of saying, okay, this is the vehicle, this is the truck this is the baggage ramp, you mentioned, you just say baggage belt appeared or a fuel loading truck appeared, and then later on it disappears again. So you're only labeling or annotating frames with those events, right?
Yeah, basically only the changes. And that everything in between is filled automatically, as Santiago said.
And what type of model architecture do you need for that?
Yeah, so Santiago already mentioned that we're doing action recognition. So action recognition basically it predicts on a small movie what is going to be the what is the classification of this movie. So historically there was like a data set called kinetics, and they solved it by doing small movie classification things. Mm-hmm. And we're using the same model as well. So which has the nice benefit that the movie can actually, if you make a small clip, you can actually much better see when something is connected. Because otherwise you have a frame in which, for instance, a fuel hose is not connected yet, mm-hmm. but it's very near to being connected, just a few pixels difference. But now you actually, when the movement stops, you actually know, okay, this is the moment when it's connected. This is the moment. So it actually makes the problem also a little bit easier for the algorithm because it knows a bit more context as well. So, and I think it's much faster than, for instance, YOLO, where, for instance, the annotations part of it that would take a lot of effort to draw boxes around everything. That's too much effort.
Yeah, I can imagine, and not everybody would draw the same box around
as well, yeah.
a specific object, right? Yeah. And if your approach is like this, how do you know that the model learns the right patterns?
Yeah, so that was one of the questions we asked ourselves as well. So we were a little bit suspicious. For instance, if the aircraft appears and then the first thing that happens is they connect the fuel hose to the aircraft, how do you know that that is actually detecting the fuel hose and not the aircraft? It could be extremely interesting to actually know, hey, we connected the fuel hose a little bit too late, because that could be a cause of delay. So we actually looked into the algorithm itself, and we managed to get like a small movie out of it, where we on the right side you see the actual the images, and then on the left side we have the same images, but they're now completely gray, and we're going to highlight whenever we are detecting a belt loader. Mm-hmm. I took the belt loader because it's slightly more interesting to see it than the fuel than the power connects, because it's the power connects is just at the nose, and that's it. So we can here see that the algorithm has nicely learned that the belt to focus on the belt loader. We shall see that it moves in a bit, and then you can actually see that the algorithm tracks the belt loader itself.
Oh, really?
Yeah. So. And that's a nice thing. So we don't even use object location. We never have specified where it actually is, and still it manages to find out where to focus on and what things to highlight.
Yeah, because that is what changes in the image, and
so it needs to correlate it to something, and it's actually that thing.
Yeah. Oh, wow, great how it indeed becomes visible like this. And it's gone. Great. Hey, and what is the most vital component of this big setup? I mean, you have cameras, you have models, you have backend. Many things need to be connected together.
Yeah, we don't think it's a model, actually.
No?
No.
I would have thought so.
Yeah. But well, it's not. I think, it's something else. I don't know.
Yeah, so basically, typically, how, at least in my experience, data science projects have worked is a model-centric approach, right? Yeah. So you have data, and you try to different models with different parameters, and you play around, aiming to improve the performance of the model, right? For this project, because we decided to change that paradigm and go to a data-centric approach. And Marcel, you can help me with the next slide. Yeah, so basically in this new paradigm, what we do is, we have a model that works well, good enough for our case. Let's improve the quality of the detections by actually improving the quality of the data. And not only the quality of the data, but the amount of information that this data contains. So, in order to do that, we have developed 4 chapters, so active learning, error analysis, monitoring, and diversified data set. And for example, with error analysis, what we do is, as the name suggests, we see in the train and validation set where the model and the labels diverge, right? So in the validation set, we automatically generate movies from those sections. Mm-hmm. and we analyze those. So basically with two intentions. So the first intention is to understand model failure, right? So for example, if we are having a generalizing problem with a new fuel truck that is not in the training set, right? Or if, for example, lighting conditions are affecting somehow the performance of the model in some edge cases. But the other part, or the other use that we have for this error analysis is basically we know where there must be mislabeled data. So we identify those sections, we give it back to the annotation team. They basically define if, okay, could be a problem in the definition or could be effectively an error in the label.
Yeah.
You know, it's a
happen.
human process. Yeah, it's totally normal. And so they correct, we close the loop, we retrain the model, and we repeat, right?
Yeah.
So with the intention of progressively keep improving the quality of the data and therefore improving the detections. The other part is also, for example, error and active learning. Basically, there we are interested to know the amount of information that detection contains. So we are detecting probabilities. That's the output of the model, the raw output, right? And you can imagine if a region is around 0.5, you know, for a certain period of time, it means that could be like there are occlusions or it's raining and the model is highly uncertain, but could also be that the model is not capable to generalize well enough this part of this specific part, right? So we try to get this in certain periods, query it, label it, and also retrain the model, expecting that for this particular case the model will perform better.
So you keep on improving by applying.
And so in addition, we also have monitoring. So that works on the production data without any labels, and there we basically have, if you don't have labels, how do you know when something is wrong, right? So we again use this uncertainty metric from the model. So if the model outputs values close to a half, we and for a longer period, then we highlight those regions. In addition, we also have a couple of business rules, and those business rules actually make sure that we can define some regions where we know that the detections don't make sense. We can also highlight those, and then we study those via a dashboard. We created small internal dashboards, and we look at those, and we learn in what situations we need to gather more data, for instance. And the final thing is that we have indeed the diversified data that we is part of our validation data set. So we regularly visit it, and basically it's a data set that is made diverse versus a lot of things that drive the scenery of the turnaround. Like for instance, what is the airline? What is is it the wide body versus narrow body? Is it big plane versus small plane? For the is it at what ramp is it connected? What are the weather conditions? Stuff like that. So we try to make it as diverse as possible, such that we can know for certain if we're improving or not. It could be that we're active learning provides a lot of narrow bodies, but then the first data set will make a drop there. So,
And by narrow bodies, you mean a certain type of plane?
Yeah, it's
right?
a small plane. So it's a little bit jargon. Wide body is a big plane. Narrow body is a small plane.
Okay. Good to hear. Hey, and it sounds to me like we used to joke that 80% of our time as a data scientist is spent on the data and 20% is spent on actually building a model. You're actually taking that in the data-centric AI approach. You're using that given, that fact more or less, turning it around and saying, okay, well, if that's the case, well, why not make data our focus and try to see if we can improve as much as possible from the data, either generated or used. Hey, and, you have a lot of components in place already. Where do you want to, and it looks fantastic, where do you want to improve still?
Well, basically what we are, the current setup, we are labeling complete turnarounds. And that makes sense, especially at the beginning of the project, because you want to train the model with what is a normal turnaround, right? You want to start with this baseline and having a strong. However, in this part of the project, we already have a strong baseline, so we need to start fighting the long tails, right? So basically, through all this machinery, we are working towards only get very specific regions in the data to be labeled, and do that constantly, like in very close cycles. Retrain the model, label, retrain the model, do a data-centric approach, and then repeat. That's what we have been working very hard the last months.
So try to get that feedback loop in place. Thinking about that a little bit more, doesn't that introduce some kind of model-induced bias or something?
That's definitely a risk.
Okay.
And it's hard to really control it if you don't know it, right? So in order to avoid this situation, we work with the diversified data set, which is not related or correlated with the model output, but it's more like, okay, we want to have as much diverse scenarios as we want. And if we start seeing a deterioration, which is not the case, but could be perfectly the case, while retraining the model and deploying, then, okay, we can act. So the message is like we actively have work towards avoiding this kind of situation.
Great, thank you. I think, given the time, that's more or less all we have time for. Looking at the audience for questions. There's one question. Do we have a mic? Looking at the stage manager, where are you? There he is.
Yes, thank you. Yeah, thanks for your talk. It's very nice to see such a deep learning application in practice. I actually have a question about the error analysis and how you would efficiently do that, because you can't just go and watch like the whole footage again and see whether the labeling is right. Do you also do that with like the probabilities, like you do with the active learning, or is there another tactic that you use there to do it a bit efficiently? Of course.
You want to take it?
So basically, thank you for the question. So basically, the difference that we have with active learning is like with error analysis, like basically we have labeled data, right? So we need to leverage over that. What we do is we don't care if, for example, there is a couple of frames that there is a mismatch, right? So we go first for the big, more representative, like, for example, if the models and the labels were off for, 5 minutes or so. So we first focus on those ones, the big parts. Then it gives us quite some information about how the model is behaving, or even detect mislabeled data. And then, so that's the way to make it efficient. So we don't go for the details for a couple of frames off, but for the big parts. That's it.
Awesome, thank you.
Yeah. One more question.
Thank you for your talk. You are using deep learning. How did you, you're talking about labeling, but how to practically set up a good labeling strategy? Do you have a dedicated team for this? I was just trying to translate it to my own business, and that's always the difficulty, right? To get enough training data.
So we have 208 days of data, so we already have quite a lot. So one of the things that indeed, it started small, of course. It was before I joined the project, it started with an Excel file and timestamps in there of when something happened. And then, of course, this takes too much time. So an in-house labeling tool was indeed developed. So it's just a couple of clicks in order to make an annotation. So that makes it easy. And I think you should also, I think that's what we did very well with our project, is that we decided to actually let the model architecture be changed such a way that the labeling becomes more efficient. And so we actually have an architecture that only predicts when something happens and not where it happens. Because if you do where it happens, if you make these boxes around it, then you spend a lot of time just drawing these boxes all the time, and that doesn't scale very well. So the setup of the architecture is very well to, the annotations it needs are as cheap as possible.
And you also take care of the retraining in that way, because I think you also probably, when you bring something into production, you also need to take care of retraining, right?
Yeah, we need to retrain it regularly. That's maybe another thing that I think that also we solved quite well in this project, is that we have one model for all the 33 tasks. So we only have to babysit one model. And there's another thing. We also try to, and this one model is now also being applied to multiple peers. So we have basically one model in which everything works together for that one model. And I think, so we're very efficient with annotations.
And perhaps in addition, it's good to mention that another challenge that I think was very particular of the project. This project was to actually have the definition right, because like with object detection, it's just okay, the object is there, right? But how then you know what a task? Because we are not only detecting if the object is present or not, but also if it's executing certain activities. So for us, getting that right was challenging, but also and was very important experience. And we also only get to that point by, for example, seeing how the model was failing. Then we knew that our definitions were not strong enough in certain cases, and we changed proactively. So that's also an important part of the whole labeling process.
Okay, thank you. I'm afraid that's all we have time for. I want to thank our guests, Santiago, Marcel, for your great presentation, great visualizations. Also tied in really nice with the previous talk about sports, also very visual. Talk about metadata and the use of that metadata to enhance whatever process you're interested in, be it sports or in this case the turnaround process of airplanes. We're going on a quick break right now, but after the break I will be joined by two guests from Adevinta, and we're going to talk about migrating from on-prem to cloud. Thanks for watching.